All right, this is lesson 3b.1. So this is kind of a continuation of our equations unit. It's just an application of solving equations. So we put it in here at this point. This is an 8th grade topic. It's called Pythagorean theorem. So a quick little note, we are in the advanced mini unit Pythagorean theorem packet. It's a blue cover page. And this packet, because it is a mini unit, is going to include both our notes and our practice in it all together in just one spot. So we are going to kind of be flipping around and picking and choosing some stuff, but I'll kind of try to be as specific as possible as we go through everything so that you can know where we're looking. So we are in the mini unit Pythagorean theorem packet, and we are looking at page number 2 right now. At the top of page 2, you'll see some warm-up problems. We're going to skip over those and just jump right into today's lesson. So this whole entire little mini unit, about a week long here, is called the Pythagorean theorem. So basically, what is the Pythagorean theorem and what does it do for us? So the Pythagorean theorem talks about the sides of a right triangle. So this is specific to right triangles only. And it was named after a famous Greek mathematician from a long time ago. And his name was Pythagoras. So Pythagoras was one of the scholars in ancient Greece, and he led a group of scholars and led a group of people who were learning from him. And what Pythagoras did was he actually realized that there was a pattern between the different sides of the side lengths of a right triangle. So he used this relationship, and he was actually able to kind of figure out that if he took the two sides that were attached to the right angle and actually squared their lengths, and added them together, that it would be equal to the square of the longest side, which was opposite from the right angle. So Pythagoras put this whole idea into words for us and became known as the Pythagorean theorem, which gives us our mini unit. And then back in the 1800s, when we actually started using variables, they applied then using the letters A, B, and C, which we'll talk about in just a minute here. So that's a little quick background on the Pythagorean theorem. You are going to watch a video about the Pythagorean theorem too, which will give you a little bit more information as well. So on page 2, in order for us to be able to talk about Pythagorean's theorem and to work with the right triangles, we are going to quick name the parts of the right triangle. So one of the things that you do notice down here is you do have this right angle, and it's going to be marked with this little square right here. We haven't quite talked about this yet, but the right angle would be the largest angle in this triangle. And therefore, if you go across the triangle from that side, from that angle, we get to what's called the longest side. And on a right triangle, this has a really fancy name, and it's called the hypotenuse. So oftentimes we'll call this the hippo, and you can actually find cute little pictures where like math teachers have like a picture of a hippo like sitting here and there's his eyeballs, and I'm a terrible drawer, but that's kind of one of the ideas. It's just the hippo is huge and the hypotenuse is the longest side. So these other two sides actually create the right angle, and right angles make L's. And the easiest way to remember these, because they make L's, they are called legs. So this is a leg. It's actually just singular in this case. Legs together, but these are each independently called a leg. So the legs make up the right angle, and then you have the hypotenuse, which is across from the right angle, and that's the largest side for you. Two things that are special about the hypotenuse: it is the longest side of the right triangle, and it's located across from the right angle. Both things that we've already mentioned here, but just good to note one more time. So that's kind of your little intro to here's a right triangle, here's the fancy names for it. Those names and this relationship only apply for right triangles. So any other triangle that you might see out there, unless it's a right triangle, this is not going to apply to it. All right, so if you would flip over to page 3, and up at the top here, we have the formula for the Pythagorean theorem. And what it does is it takes the length of the legs, A and B, so we're going to call the legs A and B. So these are both going to be legs. And it's going to say you're going to take the length of A, square it. Take the length of B, square it, and then add them together. And what that equaled, what Pythagoras found, was that it's equal to the hypotenuse, which we call C, squared as well. Okay, so we're going to take a look at this first example, and I'm going to go ahead and have you draw in the little right angle mark here. Since these two sides make up the right angle, these are legs, and we can interchange A or B, because remember, we can add in whatever order we choose. And then going across from the right angle, that one's going to be C. So notice, first of all, that we are missing our hypotenuse here. We're going to leave C in our equation. So the first thing I'm going to ask you to do, and I'm following these steps over here, is to go ahead and write the formula. A squared plus b squared equals c squared. Please note that these variables are all lowercase letters. Do not use capital letters here. Capital A, capital B, and capital C all stand for different things. So please make sure you're using lowercase letters. We're going to go ahead and plug in, instead of A, we're going to plug in 3 squared. And instead of B, we're going to plug in 4 squared equals c squared. And we're going to go ahead and start to square these. 3 squared is 9. 4 squared is 16 equals c squared. And I'm going to go ahead and add together 9 plus 16, which will give me 25 equals c squared. This is, in fact, actually an equation, so we could have, if we really wanted to, the whole time drop a line down our equal sign. And my problem here is that I don't want c squared, I just want c, because I actually want to know what the length is. If you remember back from our number system chapter, we talked about squaring and square roots and how they undo each other. So if I take the square root of c squared, I will actually end up with c. So if you remember, square root of like 16 was equal to 4 because 4 times 4 gave us 16. So what this does is the square root of c squared is equal to c because c times c gives us c squared. Remember how this number was the one under the square root symbol. So we also then, if we take the square root of one side, we have to do it to the other side. And we know the square root of 25 is 5. So that tells me up here c is 5 centimeters. So you just solved for the hypotenuse on that right triangle. So we might not always see the actual triangle. We might actually just have letters and numbers given to us. So we're going to solve for c in both of these examples. Step 1 is still going to be to go ahead and write down your formula. Plug in what you know. So a squared, 6 squared, b is 8 squared equals c squared. If it helps you at this point to drop that line, that's fine. 6 squared is 36. 8 squared is 64 equals c squared. Adding those together, I get 100 equals c squared. I'm going to go ahead and take the square root of both sides, c, and the square root of 100 is 10. So c in this case is just going to be 10. In number 2 here, I'm going to do a squared plus b squared equals c squared. 10 squared plus 24 squared equals c squared. Again, you can drop your line at this point. Your perfect square bookmark can be helpful to you, or you are welcome to use your calculator here. So 24 squared is 576 equals c squared. So this will give us 676 equals c squared. I'm going to take the square root of both sides because I just want c and not c squared. And the square root of 676 is going to give me 26. In this case, c is equal to 26. So you'll notice on all of these examples so far that all of our numbers worked out to be like perfect whole numbers. So you can actually have decimals with these because anytime you take a square root of a non-perfect square, you're going to end up with a decimal answer. However, because the ones that we worked with here today were all ones that were whole numbers, they're special ones and we call them Pythagorean triples. So Pythagorean triples is a set of positive integers that fits a squared plus b squared equals c squared. The smallest triple is 3, 4, 5. So the cool part is, while we can have 3, 4, 5, we actually have all the multiples of 3, 4, 5. So if we double them all, we can have 6, 8, 10. And you'll notice that that does not show up on this particular list. So all the multiples of these. So and multiples, let's add that on here to our list here. So 3, 4, 5, 6, 8, 10, if we tripled it, we would have 9, 12, 15. Those are all actually triples as well. So there's really an infinite list of triples here because we have all the different multiples of all of these Pythagorean triples. So these are just the first few of them. You notice that the numbers get up rather high, rather rapidly. Common ones that we'll see are 3, 4, 5, 5, 12, and 13. Those are pretty much our most common ones, and then multiples of them as well. And you'll see those moving forward. Okay, and that wraps, actually, no, it doesn't wrap it up. We have one more part that we need to do. You can go ahead and flip over to page 4. I need to talk to you about these and before you actually do the practice packet for today. So here's the deal. If a triangle is a right triangle, then Pythag works, okay? And a squared plus b squared equals c squared. But we can also flip this around. If Pythag works, a squared plus b squared equals c squared, then it's a right triangle. And that's called a converse, okay? So this is our theorem. It's a right triangle. We can do Pythag, and then the converse of it is when we flip that around. Not all theorems and converses are true, but in the case of the right triangle, this one is. So how do we determine if it is a right triangle? Well, we need to check if a squared plus b squared equals c squared works out here. So one thing we have to remember is that c is our hypotenuse and it's the longest side. So in this first example, is a triangle with sides 4, 5, and 9 a right triangle? We are going to have to make the longest side to be c. The other two that are here doesn't matter. They're just going to be a and b. So I'm going to first write out my formula. A squared plus b squared equals c squared. I'm going to go ahead and just plug in the 4 for a, the 5 for b, and then my 9 has to go in for c because it's the longest side. Put a little question mark over top of my equal sign because I don't know if this is going to work. 4 squared is 16, 5 squared is 25, put a little question mark still, 9 squared is 81. If I add together 16 plus 25, you'll notice I only get 41. And does 41 equal 81? No. So since it is not equal, this is not a right triangle. Take a look at this one over here. You might notice that this is a multiple of a Pythagorean triple, but we're going to go ahead and verify it anyway. So my longest side here is 10. That's going to be C. These other two are just going to be A and B. So I'm going to plug in a squared plus b squared equals c squared. I'll just do 6 squared plus 8 squared equals 10 squared, question mark. 36 plus 64 equals 100. 100 equals 100, and that is true. So yes, this is a right triangle then. So if Pythagorean theorem actually works with the numbers, you do in fact have a right triangle. We're going to go ahead and take a look at word problem number 1 that's on this page as well. And it says the legs of a right triangle are equal. So given the length of the legs, find the length of the hypotenuse. My legs are each 5 centimeters, and we're going to just go ahead and draw a quick sketch here, right triangle. These are both 5, and we're trying to figure out how long is the hippo. Remember, the hippo is going to be C. It's across from the right angle. So I'm going to do a squared plus b squared equals c squared, plugging in 5 in both of these and leaving the c squared. 25 plus 25 equals c squared. 50 equals c squared. Take the square root of both sides, and the square root of 50 is not a perfect square, so I get 7.071 on my calculator. So we're just going to say 7.07. We'll round to the nearest hundredths place here, and we get 7.07c. So we'll say the hippo is 7.07, and it is lengths are centimeters here. Now that actually is the end of the first part of this lesson for Pythagorean theorem.